Let's see what statistical thermodynamics can tell us about entropy. So, as we've done, we've considered a system of an ensemble of A isolated, capital A isolated systems, and all of them are identical systems. Each has an energy and a volume, and is defined by the number of particles n. And remember, these energies are nothing but solutions of the Schrodinger equation for the particle in a box, as we were looking at. It could be any of these energies. These are just solutions of, these are just quantum mechanical solutions, right? And the various systems, let's consider them to be distinguishable. And we have many different systems, a lot of these systems, and they are in different energy levels, right? So there are lots of these energy levels, and all of these systems are in different energy levels. Let's say that we have A1 systems in state 1, A2 systems in state 2, AN systems in state, the nth energy state. Hmm. So, how many ways can I make this arrangement? Okay, now, this is given very nicely, and if you're interested, look at the maths chapter just preceding the chapter on entropy in Macquarie. This is given by the formula where W, the number of ways that such arrangements can happen, is capital A factorial by A1 factorial, A2 factorial, so on and so forth. In fact, you already know this formula when I have only two systems, then it's n factorial by, let's say the two systems are divided by n minus L and L states. So n factorial by n minus L factorial and L factorial. So this, when extended to a lot of systems, then it turns out that in the denominator, well, right, if it was just two systems, it would be A1, A2, which is n factorial and n minus L factorial, as I'm saying now. So it just goes on A1 factorial, A2 factorial. I could write that as the product of all aj factorials. Okay. Now think of a system where all these systems, all of these systems are in the same state, in the same energy state, right? Let's call that A1. Now, with all likelihood, if they have to be in the same energy state, they should be in the lowest ground state. That's what should be possible, if at all. Uh, Later on, we'll see that even that is not possible. But anyway, let's see that we have all the systems in the state A1, whatever that energy state is. For the moment, let's not worry about it. So the rest of the energy states are all 0. So nothing in state 2, nothing in state 3, nothing in any of the other states. If I do that, then A1 happens to be A and 0 factorial is 1. So A factorial by A factorial, W is just 1. I have only one way to, to arrange my systems. Right? This is a complete ordered state. I just do not have no other possibility. So no disorder at all. This is the only way I can arrange. Okay. And one can show that, although we are not going to show, one can show that if all of these A's happen to be equal, then we have a totally disordered state. Okay. Maximum disorder is when everything is just scattered. So W happens to be a measure of the disorderness or whatever. Let's define entropy to be proportional to W. And the way it was defined was Kb log W. Why log W? Because if you think of two things, okay, two systems, A and B, and A is disordered by an amount WA and B is disordered by an amount WB, then the total disorder should be WAB. So if the number of ways I can arrange A and the number of ways I can arrange B is given by WA and WB, then the number of ways I can arrange AB, yeah, when they're distinguishable, of course, is WAB, right? So as I want my entropy to be additive, so my disorder should be additive. And when I take log of WAB, what I get is log of WA plus log of WB. So entropy of A plus entropy of A is equal to entropy of AB. Yeah, this is what we want. And that's why log W is taken rather than W. Now let me start to use these expressions over here in case of entropy. So S, entropy is now given by Kb log W, which is Kb log capital A factorial by product of Aj factorials, right? So I can write this is equal to log of A capital A factorial minus Kb. So the summation, because it goes over to log, the product, log of product becomes sum of logs minus kb sum of log aj. So which becomes equal to kb a, well, this particular term, log of a factorial becomes a log a minus a. This is from something known as the Stirling's approximation, this which is also given in the maths chapter before the entropy chapter. So the Stirling's approximation gives log of n factorial is equal to n log n minus n. And so it gives you log of a factorial is equal to a log a minus a and multiplied by kb, of course. And likewise, log of aj factorial, well, there should be a factorial here, is aj log aj minus aj. So the summation remains and minus becomes plus. And the multiplication with kb, of course, remains. Now, sum of aj is nothing but capital A. So there comes out to be plus kb times capital A, and we had a minus kb times capital A. So I can take these and cross them out. What I get is kb A log A minus kb summation. Wait, these come here. Okay. So we have kb capital A log A minus kb summation of small aj log aj. That's what remains. Okay. Now we know that the probability of the system being in state J is given by aj divided by capital A. This is something we have seen in a couple of in one of the first lectures where we have defined the ensemble. So I could replace aj with pj times capital A, and if I replace that over here, then what I get is Pj times capital A log of Pj times capital A. Okay. Further simplifying it, what I get is Kb A log A minus Kb Pj A log Pj minus Kb Pj A log A. Right? I just split this log Pja into two terms. And what is this? A log A doesn't A log A doesn't depend on the summation. It's independent, so I can take it outside. So and sum of Pj over all j's should be equal to 1. So this should be minus Kb A log A, and then I have a plus Kb A log A that gets cancelled. What I'm left with is S, which is for the entire ensemble, right? That's where we started because I had many different ways of arranging all the systems in the ensemble. So S for the ensemble is minus Kb summation Pj A log Pj. This middle term is what is left over. Okay. And if I divide the entropy of the ensemble by capital A, that is the number of systems that I have, then I get entropy for the system, which is nothing but minus Kb sigma Pj log Pj. So I get entropy in terms of the probabilities of occupancy of the states. So if all the probabilities except one is 0, right, what I get is log of 1. That's the only term that survives. Comes out to be 0. So S of system is 0. It's a perfectly ordered system. And again, as we could show earlier, that if I had equal distribution, I can again show that if all the pj's are equal, then I have maximum disorder in the system. All right. Now, how does entropy and partition function? How can I relate entropy to partition function? I've seen that I've taken all the thermodynamic parameters or thermodynamic quantities and related them to the partition function. So we go back to this particular equation. The system entropy is given by minus Kb sigma Pj log Pj. And I can write Pj in terms of the partition function. I know it is e to the power minus beta Ej by capital Q. So we've seen this. This is the definition of Pj as we had seen in the first lecture on thermodynamics, and log of Pj. So if I can write it like that, I can further split this log of e to the power minus beta Ej, which is minus beta Ej minus log of Q, right? And the first term over here, I can get beta outside the summation. So I get beta minus beta kb outside the summation. So I get beta kb sigma ej e to the power minus beta ej by q. What is this? Sigma, sorry, only the first term, huh? Only the first term summed over here. Sigma ej e to the power minus beta ej by q is nothing but the average of the internal energy, and here I have kb log q by q sigma e to the power minus beta ej. What is sigma e to the power minus beta ej? That is essentially the definition of q. So I have, what I'll be left with is just kb log q. So this is the internal energy, beta kb I can write as 1 by T. So internal energy U by T plus Kb log Q is what is left over. Right? And U, we know from the first lecture itself, is nothing but Kt square d log Q by dt. So divided by T becomes Kt d log Q by dt plus Kb log Q. I have an expression for entropy S system in terms of Q completely, right? I can of course write that as minus d log Q by d beta as well instead of Kt. Okay. And the last thing that we look at over here is how do these two correlate? The molecular entropy that we've shown here, which is minus Kb Pj log Pj, sigma Pj log Pj, and the classical one, which is dq reversible by T, right? So ds, if S is given by this, then ds is given by ds by dpj would be given by 1 plus log pj. So ds is given by minus kb sigma dpj plus log pj dpj. Okay. Now sigma of dpj is 0 because if the probability of one of the states goes down, the probability of the other one increases. So the net change is 0. And sigma of pj we know is 1, right? So ds comes out to be minus kb sigma log pj dpj minus kb, which becomes, I substitute pj with e to the power minus beta ej by q, and then I again take the log. What I get is minus beta ej minus log q if I split this term. So I have minus kb sigma of minus beta ej minus log q dpj. And log q is a constant, so sigma of dpj would go to 0. So the second term would go to 0. What I am left with is minus kb minus sigma of minus beta ej dpj. So, and beta is again a constant, so beta I can get out. So what I'll be left with is beta kb, right? Sigma ej dpj, right? I've just written the variables here. So the change in entropy is just ej dpj. And ej dpj is something which we have seen in the last lecture. It is equal to the this entire sum. This is equal to the heat exchange reversibility. So what I get is ds is equal to beta kb q reversible. And classically I know ds is equal to q reversible by t. Now equate both of them, and what you get is something we've been using for quite some time. Beta is equal to 1 by kbt. Thank you.